Howdy, everyone. Happy end of the week. This cartoon I put up reminds me of a movie from some years ago called IQ. It was quite cute. It had if I remember correctly, auto mechanic who fell in love with Einstein's niece, and turns out the auto mechanic was super good also at quantum mechanics. Also, for those of you that are interested, today is Oprah Winfrey's 57th birthday. She's one of the richest women in the world. She's worth around $3 billion. Her salary is about $200 million a year. But that, of course, leaves her well behind people like Jeff Bezos and Elon Musk and Bill Gates. So if you feel sorry for her, feel free to send her a check. Okay, so that's enough of the practical stuff. Let's move over back to quantum mechanics. And where we got involved with last time is we started talking about a particle in a box. So I'll just remind you about the details. So we're dealing with one particle, presumably something like an electron. We're in one dimension, and we're saying that it's stuck in a box. Within the box, there's no potential energy on the system. So capital V is equal to 0. Outside the box, the potential energy is infinite, so nothing can get outside the box. So what we're going to discover, or what we do discover, is that we have boundary conditions, that the wave function for the electron in the box has to go to 0 at the walls. Wave functions are required to be continuous, and the wave functions have to be 0 outside the box in order to make the probability function psi squared equal to 0. So we went through some mathematics. We applied the boundary conditions. This is what we came up with as a starting point. And when we applied the boundary conditions, even though we wanted to start as a possible function was a sine term plus a cosine term, we saw that the cosine term was not valid because it would not have gone to 0 at x equal to 0. So that gave us one of the boundary conditions. And then the other one came from the fact that at the right wall, the wave function again has to go to 0. And so that made the function sine k of L equal to 0. And we saw that this would work if k times L was equal to a certain integer number of radians as such for the wave. So when we plugged that in, we got what the wave function was, and then we could plug it into the expression we had previously for between k and E, and that gave us ultimately what the energy levels were for the system. And I think that's about as far as we got last time. So,
Professor?
Yeah.
I believe the class is saying that we did not go over this part yet. We were a little bit further back. Normalization, something.
Page 26.
Yeah, 26. Page 26. Was it?
Okay. Okay. Well, maybe I went over this a little bit too rapidly then, but I'll just repeat again what I said. A situation in the box is capital V is equal to 0. We've solved that kind of problem before, but here we're wanting to look at possible solutions for it. So we'll write it as a sum of sine and cosine terms. From previous results, and I do know we went over this, we had a value for what k was. The important part that I was just mentioning is one of the postulates of quantum mechanics says that wave functions have to be continuous and they have to be single valued. So the continuous aspect says that since no particles can exist outside the box here to the left or the right where the potential energy is infinite, psi squared, the probability function has to be 0, and so we know the wave function is 0. So that means when the wave function out here to the left is 0, gets to the x equal to 0, where it joins up with the wall, the wave function within the box has to start at 0. So that's called a boundary condition. And so that's the situation right here. Psi of 0, meaning psi at the x value equal to 0, has to be 0. And so we can plug this into the general solution that we have, that I gave you as something that would work without boundary conditions. But when we put in x equal to 0, we see the sine term goes to 0, but cosine goes to 1. And so that dictates that the coefficient for the cosine term has to be 0. We all know that the cosine of 0 is 1. So we could have guessed that ahead of time, that we know the function cannot have a cosine term in it if x0 dictates psi to be 0. At the right wall, again, x is equal to L, we have another boundary condition. And so we can plug into what we have left for the formula. And so we will get at x equal to L, A will be equal to sine of KL. So the coefficient A is going to wind up being a normalization constant. So that's not going to be 0. So we know that KL has to make the sine equal to 0. And the way you make sines equal to 0 is taking the sine of pi radians or 2 pi radians or 3 pi radians and so on. In principle, mathematically, you could also have sine of 0 go to 0. But if you always made sine of 0 without a KL in there, then you would not even have a function at all. So in order to have a particle, we have to start at pi radians or 2 pi or 3 pi. Okay, so this dictates what KL is. It has to be an integer number times pi. And so we can solve for K. At what we looked at last time, we saw what K was, and that's this expression here. First, what I do is then I plug in for K into the wave function solution that we have. So we had sine of Kx, but now I plug in n pi over L for K. So we have a wave function for this state. All right, well, since we know what K is, and we know what the energy levels were from before, I can take the K value up here, n pi over L, plug it into this expression, rearrange the terms, I get a solution for the square root of E, and these come out to be the possible energy levels that you can have for translation. I'll mention this again later, but notice that the lowest energy level will be something positive. It won't be 0. So for translations, we're again going to have a 0-point energy that you can not get rid of even at 0 degrees Kelvin. But these are going to be the only energy level values allowed for the particle in the box. Okay, so hopefully, if we didn't get this covered last time, that'll be enough that you can see what's going on. All right, well, we should always normalize our wave functions. So this is our function up here, and that's what we need to get normalized. So we'll just keep A here as our normalization constant. Normalization means we integrate from minus infinity to plus infinity, and we want the product of psi star psi, which here is just going to be psi squared. We want that equal to 1. Now, I've already pointed out that in the region to the left of the box and the region to the right of the box, the wave functions are 0. So if we separate the integration into 3 parts, we can throw out the part to the left of the box and the part to the right of the box, because the area under the curve, which an integral is just going to be 0. So we wind up just having to integrate from 0 to L within the box of this wave function. Okay, so this is the formula that we have. I plug in the sine function, and so we need this to come out equal to 1. I mentioned before that the back of your lecture notes have integral tables. Anytime on an exam or anywhere you need an integral, it'll be given to you on the front page. If you're doing a problem in the book that you need an integral for, you can look at the back of the lecture notes and do that. Okay, the integral table gives you this. And by the way, I might point out, if you go to typical math integral tables, they will have sine squared of x dx. And then it gets a little bit nastier for you that you have to figure out what happens with the a. So I'll try to be friendly for you and show you what happens when you have some multipliers in here like the a times x. Anyway, this is what you get from the integral table. If you do a comparison, you'll see that our a is n pi over L. So this is what we have to evaluate. So we have to evaluate it from x equal to 0 up to L. So we first look at the cosine sine term, and then we look at the x term. At x equal to 0, the sine term here goes to 0, so we know that drops out. And we know 1/2 x goes to 0. So we get no contribution from x equal to 0. At x equal to L, you'll see that we wind up with sine of n pi again. And the sine of n pi again is 0. So again, the cosine sine term doesn't contribute anything here. And so we only wind up plugging in L into 1/2 x. So we get L over 2. So L over 2 has to equal 1 for the, a squared times L over 2 has to equal to 1. So this is what we have. We solve for A. And so the normalization constant for psi is 2 over L to the 1/2. I think some problems that have been assigned for you in the book ask you to figure out what fraction of time an electron would spend in a certain region of the box. You would then just take a function like this, and if it gives the region, say, from 0 to L over 4, you would just, instead of integrating from 0 to L, which would come out to be equal to 1, you would integrate from 0 to L over 4, and it'll tell you the fraction that it's in that part of the box. It won't be 1/4, as you might logically guess. It'll be something else because quantum mechanics takes into account the wave properties of the system. So it's quite common for me to give you a question on normalization on the first exam also. And hopefully you find it pretty much straightforward. If you're rusty with looking at integral tables, or if you're rusty at taking derivatives, I recommend you go back and practice on that. Some chats have popped up. People agreed that I needed to go back, and so hopefully I went back far enough to get us started on the particle in the box. Okay, now one thing that I could have done up here, after we had the wave function and a value for k, I simply plugged back into these two expressions and solved for what the energy level was. What you can always do, once you know the wave function for a quantum state, you can plug it back into the Schrodinger equation and figure out what the energy levels are. So this is what I'm going to do here. I'm going to take this function and then put it back in the Schrodinger equation. So here's our wave equation. Capital V is equal to 0 within the box. And we first need a second derivative, as you can see here. So here's first derivative of the sine of n pi x over L. This term comes out in front. I take the second derivative, and I get a minus sign of the same thing. And again, I get another n pi L in front. And what you should notice when we're done with this, here's still the normalization constant. Here's the original wave function. We just get a constant times psi. In this case, it's n pi over L, that quantity squared. So I'll now plug this in. And when you do this, you have to be a little bit careful because remember, h bar involves a 2 pi over it. So to get it to all come out, I need to expand h bar squared into h squared over 4 pi squared. H bar, remember, is H over 2 pi. So here I've expanded it, also included the 2m that I had on the bottom. You'll see my pi stars cancel out. And all of the translational levels are going to be given by n squared h squared over 8ml squared. Now this is kind of an unusual case because it's just a straight formula. We don't have to have a separate wave function generated for each state. We have them in general with just the n in there. And then we're going to get a general solution for all values of n. So n can be 1, 2, 3, 4, whatever. For the first state, it'll be 1 squared times this quantity. Next one will be 4 times that quantity, and so on. The corresponding wave functions, you see they also change. For the first one, it'll be the sine of pi x over L. For the second one, it'll be 2 pi x over L. So all of the wave functions will be different, but they can be given by a uniform formula with an n in there, where the n is going to be an integer quantum number. Okay, so let's look to see what the solutions actually tell us. And here I've fairly crudely drawn a picture for you, but this is the way that we often like to represent quantum mechanical problems and the solutions. So first of all, we present the potential energy curve, and that's what these arrows and the line on the bottom represent. So potential energy goes up to infinity at the walls. Zero energy is down here. And then at different n values, we will have different magnitudes of the energy given by n squared, h squared over 8ml squared. So this will be the quantity in parentheses here times 1. If I go to the next quantum state, it'll be 4 times that energy. The next one will be 9 times that energy. The next one will be 16 times that energy, and so on. Also in convention, we like to draw the wave functions. And here I've drawn psi 1, the way it's going to look. And then I've drawn psi 2. And actually I've drawn psi 1 upside down from the way of it in the sine function. But I might mention this to you now. Whenever you change the sign, SIGN, for a wave function, it doesn't matter because the probability is the wave function squared. And anything you do to, in order to try to find average values and so on, it's not going to affect the situation. So I could have drawn psi 1 as coming down here at negative x and then going positive at positive x. Psi 2 starts looking like this. Last time I went through a little derivation just to show you that as you start getting more and more kinetic energy, the wave functions get more and more squiggly or more wavy. So notice this is just kind of a lump, and then we have 1 wave here, then we have 2 or 3 waves, however you want to look at this. But these are sort of wave packets that we have. They aren't free open waves that you have, but this is how they'll work their way up as the functions. So this picture basically gives us the entire view of what's going on. This is a particle like an electron flying around. It cannot have arbitrary energies. It has to have any of these energies given here by this formula, but nothing in between works. Just some comments. The first one's not particularly significant, but notice that the energy levels start spreading out. I already mentioned number 2, the wave functions have increased curvature, they become more squiggly, as higher in n indicates higher kinetic energy. So here's this particle flying around, and later on we can look at how we would be calculating the average kinetic energy of an electron in this state, or the next state, or the next state. But right now we can just see from the squiggliness that the kinetic energy is going up. Also notice that every other function is even with respect to the center of the box. In other words, if we cut the first one in half, left side and right side are mirror images of each other, so they're just the same. Same one for the third level, they're mirror images of each other. The second one, the fourth one, sixth one, so on, they're going to be odd functions. So if you reflect one into the other, one side is going to go into the negative of the other. Someone asked whether the lowest energy level should be subscripted 0. No, it should not, because we're writing the energy levels. I should have put a subscript n up here, or I could have put a subscript n here. The way I've done it is so that the subscript corresponds to the quantum number n equal to 1. There is no quantum number n equal to 0. So that's the problem here. For harmonic oscillators, we did have a quantum number v equal to 0. That was the lowest thing. When we get to talking about the hydrogen atom, the lowest quantum states are going to be for n equal to 1. No 0 again. So sometimes the lowest state will be 0. Sometimes it's going to be 1. In this case, it's 1.
I was talking about the wave function psi, the subscripts on them. I think they're off on what you have written. On the graph, scroll down. The function subscripts.
Oh, okay, you're right. There's a mistake. This is psi 1, this is psi 2, and psi 3. So, sorry, thank you for the correction. So, change this to psi sub 2, this is psi sub 3. The first one's correct. Someone asks, what is the E equation if E is not equal to 0? If it's equal to a constant, simply we could put E minus V on the left side. If it's equal to something more complicated, then we have to do more complicated math to get the answers. But for convenience, we just set it equal to 0, so we don't have to mucky around with putting in a capital B. N here does correspond to the quantum number n, but they're not electron shells. We're talking about a particle in a box. Later on, we'll talk about hydrogen atoms. We're using the same symbol n here as we will for atomic energy levels, but this is strictly a totally different problem. It's not an electron flying around an atom. It's an electron flying around trapped in a particular box. Okay, so next let's look at the psi square plots. Here we don't have to write psi star psi since we don't have an imaginary part, but my not very pretty pictures show what things are like. But again, remember we had boundary conditions, so the probability of the particle being at the walls has to be 0. The wave function has to go to 0 at the walls. Well, the first one looks fairly ordinary, what you might expect. The highest probability is for the particle to be flying around nearest the center of the box. But if you get to the second level, notice it's got a node in here. So we cannot have the particle be at x equal to L over 2. So we mentioned this last time, that this seems pretty strange. If you can have a particle over here on the left and a particle here on the right, how is it going to get from the left to the right? And I'll say just a little bit more about it again. Here is psi 3 squared, and notice there are 2 more nodes, 2 more points of 0 probability, and there are actually 3 maxima of probabilities. Again, as far as problems that are assigned from your textbook, I think one of them asks, what are the most probable values of an electron in a particle in a box in a particular quantum state? So in the first one, the maximum probability is here in the center. In the second case, you'd have to find these maxima. What you would do, of course, is you would just write out the probability function, take its first derivative, and set it equal to 0. That's how you find a maximum or a minimum. For the third case, you would have minima that you can find, and you can have maxima that you can find by taking the derivative of the probability function. I have one more chat question. This is all happening in region 2, correct? No particle can be outside the box where the energy would be infinite. Okay, so back to the strangeness of these nodes. So how does a particle get from the left side to the right side? The main thing I want to point out is we are working with the time-dependent Schrodinger equation. So we're not allowing time to come into play here. So think of this as a snapshot with fixed time. If we were to look at all the particles in quantum state n equal to 2, this is how they would be distributed. If we turn the time on, the particles are allowed to switch between quantum states. And so, for example, some might go from n2 down to 1, and then back to 2 again, so they can still get back and forth from each other. But many aspects of quantum mechanics, as we've seen, including zero-point energy, they're perplexing. But again, I want to emphasize, we wouldn't be telling you about this stuff, but it all works. And you wouldn't have cell phones and DVD players and things like that if people didn't understand quantum mechanics. And as I just said, use of time-dependent wave equations help understand what's going on. This time I might point out something I like to say, maybe even several times during the semester. One of America's most famous quantum mechanicists was a fellow named Richard Weinman. He was famous enough they even put him on a commemorative stamp, maybe something like 10 years ago. Anyway, Feynman has been quoted as saying, "Do not trust anyone who tells you they understand quantum mechanics." So basically, we know we can do the math, but trying to always visualize exactly what's going on can be up for debate. So what I'm trying to do is give you the basic mathematics and hopefully also show you how it leads us to an understanding of things like atoms and molecules and spectroscopy and so on. Okay, another comment about the wave function squared, the probability function. So here I've tried to draw what the probability function would look like for psi 10 squared. So you're going to have lots of these nodes that you have. So 9 nodes if I plotted this correctly. And what you see is actually, though, that the probability starts getting more or less evenly spread out throughout the box. And in the early days of quantum mechanics, a lot of classical physicists and so on were unhappy with it. They said that we can't really believe this unless you can have equal probability for something like a particle in a box. And so this is something called the correspondence principle. Perhaps your book mentions this, but it's not terribly important. But basically it says that classical behavior is approached as you get to very, very high quantum numbers. And actually I should mention for translational energies, these energies are fantastically small. For n equal to 1, depending on the mass, it might be something like 10 to the minus 22nd joules or something ridiculously small. So you don't start getting significant translational energies unless you get to something like n equal 5,000 or 5 million or something like that. And by that time, the correspondence principle kicks in where you're going to have thousands of these little nodes almost all squished together, making it look kind of like it's a continuous probability. One other thing I wanted to point out is if you look at the formula for the energy levels, and then you calculate what the energy difference is between any 2 levels, you get this. And so you see the energy levels. First separation is 3 times the term in parentheses, then 5, then times 7. But if you go to very, very high L, and on a quantum mechanical scale, a high L is something like a millimeter. so it doesn't have to be super high in the real world. If L gets to be a millimeter, which we'll consider to be approaching infinity, delta E approaches 0. So those energy level separations, they wind up being something like 10 to the 64th joules or something like that, something just so small that we don't really need to worry about it. And what I'm saying here, large L means the container is very large, or if you have a free container, then the quantum mechanical separation of the energy levels disappears. And you'd really be back to the de Broglie formula for what the waves and energies and momenta are for this particular system. It's only when you start confining systems that this happens. Okay, this next part, I took it out of a book some years ago, but I looked at this year's version of the book, and I think it's actually in there. So just to show you that the particle in the box isn't totally esoteric, I've already told you that we will be using it later when we want to talk about statistical mechanics of particles with translational, rotational, and vibrational energy. But here's a calculation that's applicable for a significant biological molecule, beta keratin. This, as you can tell from the name, if you didn't know, it's common in carrots. It also turns out beta keratin looks a whole lot like the molecule retinal. And retinal is a molecule involved with the vision process that we have. So most of you have probably read about how vision works. I think our eye takes something like 30 snapshots a second, and then the brain merges them together, so we think we're seeing continuously. But once the eye sees this stuff and retinal interacts, you have molecular interactions and processes that take picoseconds or nanoseconds. In there, there are quite a few steps that convert what the eye actually sees into the messages it sends to the brain. Anyway, please read this, but what this shows is that, notice this is a conjugated system. And so if you have an electron in a pi orbital here, it can just travel all the way around the molecule from one end to the other. And so in this model here, you can think of this as a particle in a box. The box on the left starts here, the box on the right starts over here where the conjugation ends. So if you picture it like this, then you can do some mathematical manipulation. What you can find is this is where different electrons would be in the system. Now you're going to have lots of electrons in this system because every carbon atom is going to donate a free electron to the pi system. So you have lots of them to put in. The first one we put into the translational quantum state N1, and presumably there's just enough to give us a total of 22 electrons in the system. And so the last 2 electrons are at n equal to 11. So a possible transition that you can have for this molecule is to go from N11 to N12. And here I think they've done a calculation what the energy change would be for that calculation. Or actually they've done the calculation in terms of wavelength that you would expect to see. So I encourage you to read this. The mathematics is basically the same that we've just gone over. All right, well, we cheated, of course, but we'd stuck just one simple little electron into a one-dimensional box. But a much more realistic case would be to have a three-dimensional box. So let's just very quickly look to see how this might work. So I've told you before that if we wanted a three-dimensional Schrodinger equation, we would write a del squared psi here instead of just d squared dx squared of psi, and then have that equal to psi. And then we have second derivatives with respect to x, y, and z. Now, in this case, the wave function is going to be three-dimensional, depend on x, y, and z. And luckily, and I won't prove this to you, but luckily, you can write this as the product of the x dependence, the y dependence, and the z dependence. So I've written the x dependence as psi sub x, psi sub y of y, and psi sub z of z. All right, so I'm going to start with this equation up here, and I'm going to divide through by this entire wave function, which is psi x times psi y times psi z. So if I'm taking derivatives with respect to x, that's the only one that acts like it's not a constant. So the other ones cancel out because I have a psi up here. I mean, I'd have a psi x, psi y, psi z, and the psi y and psi z are canceled out, but the x isn't canceled out. So I think I muddled that up a little bit. We're dividing by psi. The x part gets used up in the derivative, and then the y and z parts get canceled out here. All right, well, the point is that we wind up with three parts, each giving us an x dependence, y dependence, or z dependence, and we can solve them as individual problems. And so the x dependent problem looks like this, and I think you'll notice that this is exactly the problem that we had before. Only I've got the psi x here, I multiply it by psi x, and I'll have minus h bar squared over 2m d squared psi dx squared times e, or psi is equal to e times psi. Just the problem we had before, except now we're making sure we're talking about the x dependence. Solutions, again, will look exactly the same, except I'm going to identify that our quantum number is for the x direction and our dimension is in the x direction. So the x component of the energies are given by this. I can do the same thing for x, y, and z. And then I'm going to have the energy component from x here, from y, and from z. Okay, so turns out you have basically 6 parameters that can affect what the energy levels are. So it can become very complicated. So we can have a length, width, and height that we have for the box in Lx, Ly, and Lz. They would go down here. And then we would wind up with having to use different amounts of quantum numbers nx, ny, and nz. Just to make this a little bit easier to understand, let's make it a cube that we're going to look at. So I'll have capital L represent Lx, Ly, Lz, all in the same direction. And then our energy levels come out looking like this. We'll have this term in front, and then the rest is going to depend on the quantum numbers, nx, ny, and z, all of which can start at 1 and then having to be integers. For simplicity, I'm calling this constant in front C. So here, I'll put in a little table of what the energies are going to be and in order of energy. So our lowest energy would be when nx, ny, nz are all ones, 1, 1, 1 for each of them. Total energy would be C times 1 squared plus 1 squared plus 1 squared. So our total energy is 3C, and there's only one way we can do it, and that's what we mean by degeneracy. So only one way we can do it. Well, the next highest energy state, and we have a chat question. Oh, okay. Sorry about that. Apparently, the copy center had this cut off for you. I'll make a copy of this page and I will send that to everybody. Thank you for telling me. I'll write a note to myself. Okay, so sorry about that, but what you can envision is, well, you can see my screen, so you can actually see it. The next energy level set is going to be threefold degenerate. There are three ways to do it. One of the quantum numbers has to be 2, and the other two have to be 1. But nx, ny, or nz can be the one that's 2. And so we would have a set of 3 quantum states that have exactly the same energy. They would have each an energy 6 times this term in front. If we want to know the third set of energy levels, they would have to be 2, 2, 1. And again, there's only 3 ways of doing it. If you take 2 squared plus 2 squared plus 1 squared, did I do that right? Or, yeah, okay, I did, luckily. It comes out to be 9c as total energy. Well, you can keep on going on in this table, but as you can imagine, you start getting more and more degeneracy as you have higher levels. When you get to the situation 2, 2, 2, then there's only then one way you could do it at 12c. But if you wanted to look at the whole energy diagram and putting it another way, if you later wanted to do thermodynamics of this system, we would have to consider all of these quantum states. And if the chamber we're looking at is not a cube, we'd also have to put in what these capital L values is. So this exercise on this page, it's not likely I would ask you anything about this, but I just want to show you how it's not terribly difficult to go to a real case as such. Now, I would show you nice pictures of what the wave functions look like for a 3-dimensional case, but I can't show you the amplitude of the wave and then have 3 directions, x, y, and z. So I apologize for the quality of this picture, but this is the wave function for a 2-dimensional particle in a box. So we're going to have dimensions x and y, no z direction. The up direction is just going to be the wave function. So you see it's going to have positive areas, all these white blobby areas, and then it's going to have equivalent magnitude negative areas. And this is what would apply at nx equal to 4 and ny equal to 4, one specific quantum state that we would have. Notice we also have a lot of nodes. Here's a node, here's a node, there's a node, there's a node. Lots of places where the wave function is equal to 0. So keep in mind what this means. This means where the magnitudes squared are large, that's where the system can be. So system is very likely to be there. When you square this, it's very likely to be there, very likely there, very likely there, very likely there. And it can't be here, 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 and there. So hopefully to some of you musicians, you'll think of this looking a little bit like a multitude of violin strings or piano strings or whatever. But the wave properties of the system, the boundary conditions are dictating what the wave functions have to look at. And I made a suggestion here. Go to Wikipedia and look at particle in a box, and you can get some more enlightenment about what's going on. Thank you for all the questions, by the way, and thank you for pointing out that this didn't make it. I'll have to chastise the Copy Center for not being careful with that. One of the problems, as many of you probably have discovered whenever you make copies, is sometimes the Xerox copies wind up a little bit larger and they go off the page. And I indeed have this very low on this particular page. Okay. The good news on the next page is you're never going to be quizzed about this except perhaps as a concept question. I'm going to try to give you a brief overview, but I also want you to remember that this is very, 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 very important. And in fact, I think in your notes, I'll put something about tunneling about it, but then we also talk about the tunneling electron microscope in there. So read that aspect. We're not going to go over it, but if people didn't understand tunneling, you could not build the best microscopes in the world today now that you can. Okay, our particle in the box was pretty simplified, as you saw. We said absolutely nothing can get outside the box because we made the energy outside the box be infinite. And nothing in the world, even one lonely little electron, can have an infinite amount of energy. So the realistic cases are where you're going to have some finite amount of energy that's not infinite, but in principle, it's going to be high enough that perhaps something with a lower potential energy cannot go over it. So in physics, you should have learned that if you have a hill and putting a ball at the top of the hill has a certain potential energy for rolling down and having a kinetic energy. If you try to roll the ball up the hill, if you don't have kinetic energy enough to overcome the potential energy of the hill, the ball will never get over the hill. So this is classical mechanics. Well, quantum mechanics cheats. It says if you have a hill that's not extremely tall, or if you have a hill that's not extremely thick, then particles can tunnel through it. I think I asked some of you last time how many of you have been to Europe, and quite a few people had. If you've been to Switzerland, they have incredible tunnels. They have one that's 50 kilometers long. The last time I was there was maybe 20 years ago. And as I approached this tunnel, they had these big signs saying, expect a Stau, which in German means expect a delay. And I don't like claustrophobic situations, so I said, I'm not going to go through the tunnel. And I took the long route. I think it's called Gotthard Pass over the hill. Maybe it took me half an hour longer than a normal tunnel ride would take. Well, on that trip, I went back to Ulm, Germany, and the next morning I came down to breakfast, and there was a very frazzled lady checking in. Turned out she had gone into that tunnel, and she'd been stuck there for something like 10 hours before she could get out of that 50-kilometer tunnel. Okay, well, I think electrons would not be able to tunnel through 50-kilometer hills, but they can tunnel through other things. Okay, so I may have to say a little bit more about this next time, but let me tell you what the basic situation is. So we'll have a finite potential energy. We'll have a certain width of this barrier from 0 to L. A particle like an electron is going to approach it. It's going to tunnel through section B here, just like the Swiss did, and then it's going to come out on the right side. The potential energy to the left and right is going to be 0, and in the middle, we'll say it's a capital V. Quantum mechanics for the problem on the left and right look similar. It's just the regular one-dimensional problem with capital V equal to 0. And we can write solutions like this. I gave you the solution before, e to the ikx, but here I want to add a second term that would also work, e to the minus ikx. And the same thing for the right side, that we can write these exponential solutions. If we have a fixed potential energy, then we've also solved this problem before, and we had solutions for K. And here I have a mistake in my notes. Again, I don't know if I fixed it in what was sent to you, but there should be a capital V here. It should say capital V minus E. You're not going to be tested on this, so it's not all that critically important. But what I want you to note is that each of these terms implies something. So e to the plus ikx indicates a particle with momentum going to the right in region A. When we have a minus sign in the exponent, it's being bounced back from the barrier. In the middle, if we have a plus I in the exponent, it's going to the right. If it's a minus I, it's going to the left. Then finally, on the right side, it can also have things like that. And I have a chat question. Someone asked me if I can speak Deutsch. I can speak German well enough. I had 2 years in college, which weren't all that helpful because you'd only speaking German. I can read German pretty well. But my family spent a year in Germany about 30, 40 some years ago. And I got to where I could get by. My grammar was terrible. Okay, but that was a digression, I think, trying to keep me from talking about the nasty tunneling. Okay, I'll mention a little bit more about this next time, but my point is that you can do the mathematics of the problem. And the one thing I do hope that you note is we have another boundary condition that comes out of this, which says that the first derivatives of the wave functions have to be continuous. So before, when we had boundaries like between A and B, the wave function has to be continuous, but also the first derivative has to be continuous. So we have two boundaries, one between A and B, one between B and C, and at those boundaries, we have to have continuity of the wave function. When you do that, you can write all these nice little expressions here, try to solve what's going on. And ultimately, if you're clever enough and work with this stuff long enough, you build yourself an electron tunneling or tunneling electron microscope. So maybe I've said enough about tunneling. I'll try to show you a picture or two of it next time. I can take more chats or more questions if you have any. Someone asked how gravity influences wave functions. The answer is gravity is one of the most misunderstood things about anything nowadays. Maybe we'll chat about it some future time. In all of these problems, we are assuming there is no gravity effect. I hope most of you have seen that in the last several years, people have detected gravity waves. These are measured by Fourier transform, massive spectrometers, one in Washington State and one in the swamps of Louisiana. And they can detect these things when a couple of black holes collide. Black holes collide maybe several times a year. There are billions and billions and billions of galaxies. In fact, there's trillions of galaxies. And so even though these black hole collisions are rare, when they do occur, these sites are looking to measure them. And I've lost count. The first sighting or the first measurement of observation was maybe 4 or 5 years ago, but now there are at least 4 or 5, maybe they're even up to 10 at this point. So they are studying the effect of gravity waves. Gravity, by the way, is also, it's carried by waves. They're not electromagnetic waves. They are more in the acoustical region that we work at. So it's like a low bass on your stereo music player and stuff. So gravity is still a very complicated thing to be aware of. Okay, I had another question. Do we get the shape of electron orbitals by integrating with wave functions? The answer will be yes when we get to talking about wave functions for orbitals. Right now we're talking about a particle in a box, so we won't get it from right here. Okay, stay healthy, everybody.